Welcome to AI Frontiers, where we explore the cutting-edge developments shaping tomorrow's technology today. Today, we're diving into a robotics revolution that's transforming machines from rigid, programmed tools into conversational, intelligent companions. On October 28, 2025, researchers published 12 groundbreaking papers that collectively represent a quantum leap in robot intelligence, moving us from commands to genuine conversations with our mechanical helpers. Picture this scenario. A robot in your living room that doesn't just follow pre-programmed routes, but actually understands when you say, "Go grab my reading glasses from the nightstand." It doesn't need a map with precise coordinates or a lengthy setup process. It simply gets it, just like a helpful houseguest who knows where things are and responds naturally to your requests. This isn't science fiction anymore. The breakthrough research we're examining today brings us tantalizingly close to this reality, fundamentally changing how we think about robot intelligence and human-machine collaboration. What makes today's collection particularly fascinating is how these researchers are solving problems that have puzzled the robotics community for decades. How do you teach a robot to navigate using everyday language? Can machines learn complex behaviors without watching thousands of hours of human demonstrations? What happens when a robot needs to juggle multiple contradictory tasks simultaneously? The 12 papers we're examining today represent more than incremental improvements. They're paradigm-shifting advances that could transform robots from rigid, programmed machines into adaptable, intelligent companions that understand us as naturally as we understand each other. Think of computer science robotics as the ultimate interdisciplinary playground, where the digital world collides with physical reality in the most spectacular ways. If traditional computer science is like composing beautiful symphonies in the abstract realm of algorithms and data structures, then robotics is like conducting that symphony with a full orchestra in the middle of a thunderstorm. Every theoretical concept must survive contact with the messy, unpredictable, gloriously chaotic real world. Unlike purely computational problems that exist in the clean, deterministic world of processors and memory, robotics researchers must grapple with sensor noise, mechanical wear, environmental variability, and the fundamental challenge of translating digital intelligence into physical action. What makes this field particularly compelling right now is how it's evolving from laboratory curiosities to practical systems that could genuinely transform society. The first major theme reshaping robotics is multi-modal and language-integrated navigation, where robots are learning to understand and respond to natural language commands while seamlessly integrating information from multiple sensors. Imagine teaching a child to navigate not just by showing them a map, but by explaining landmarks, describing relationships between objects, and helping them understand the semantic meaning of spaces. That's exactly what researchers are achieving with systems like LagMemo, which combines three-dimensional scene understanding with language comprehension to enable robots to navigate toward goals specified in everyday human language. This represents a fundamental shift from traditional navigation systems that require precise coordinate specifications towards systems that can understand and respond to the kind of natural language instructions humans would naturally give. The second theme focuses on bridging the gap between synthetic and real-world training data. Traditional robotics has faced a fundamental bottleneck. Real-world training scenarios are expensive, time-consuming, and often dangerous to collect, while synthetic data, though abundant, often fails to capture the complexity of reality. Think of this challenge like training a chef using only cookbook descriptions versus actual kitchen experience. Researchers are developing sophisticated methods like the ZTRS framework, which demonstrates that it's possible to train autonomous driving systems using only reward signals without requiring expert demonstrations. This breakthrough is achieved through exhaustive policy optimization, specifically designed for scenarios with innumerable actions and rewards, combining the scalability of synthetic data while maintaining the authenticity of real-world experience. Advanced perception and representation learning forms the third theme, where robots are developing increasingly sophisticated ways of understanding their environment. Rather than simply processing raw sensor data, modern robots are learning to build rich, semantically meaningful models of their world. It's like the difference between a tourist with a camera randomly taking pictures versus a local artist who understands the deeper meaning and relationships within a landscape. A significant breakthrough involves the integration of vertical angular sensitivity into boundary vector cell models, representing a major advance in biologically inspired robot localization. By incorporating three-dimensional boundary detection capabilities, researchers have shown that robots can achieve significantly more accurate spatial localization, particularly in complex three-dimensional environments, solving spatial ambiguities that have long plagued traditional two-dimensional systems. The key findings emerging from this research collection represent genuine breakthroughs that could fundamentally change how robots operate in our world. Perhaps the most significant is the demonstration that robots can successfully navigate using natural language commands while maintaining sophisticated spatial memory. The LagMemo system achieves this by constructing a unified three-dimensional language memory during exploration, then querying this memory to predict candidate goal locations when given natural language commands. Equally groundbreaking is the successful elimination of imitation learning from end-to-end autonomous driving systems, where the ZTRS framework trains systems using only reward signals. Another major advance involves language-conditioned mixture of experts policies for multitask robotic manipulation, addressing perceptual ambiguity and task conflict challenges. Finally, effective multi-robot collaboration through distributed topological graph approaches enables teams of robots to dynamically balance exploration tasks while maintaining theoretical guarantees for consensus convergence. For our paper of the day, I want to focus on the work that perhaps best embodies the transformative potential of current robotics research. LagMemo, Language 3D Gaussian Splatting Memory, for multi-modal open vocabulary, multi-goal visual navigation by Houghty and Zhou and colleagues. This paper addresses one of the most fundamental challenges in robotics, the challenge that determines whether robots will remain confined to structured laboratory environments or truly enter our everyday lives as helpful companions. The problem they're solving is deceptively simple to state, but extraordinarily difficult to solve. How do you enable a robot to navigate to goals specified in natural language? When you tell a human, "Go to the kitchen and bring me the blue mug from the counter," they effortlessly parse this instruction, recall the layout of your home, navigate to the appropriate location, and identify the correct object. For a robot, each step of this process has traditionally required separate, complex systems that often fail to work together seamlessly. What makes Zhou and his team's approach revolutionary is how they've unified these traditionally separate problems into a single, elegant framework. The magic happens when the robot receives a navigation goal specified in natural language, as the system queries its language-aware spatial memory to predict candidate goal locations that match the linguistic description. The system gets really clever through what the researchers call local perception-based verification. As the robot moves toward its predicted destination, it continuously validates its understanding of the goal, using real-time perception to confirm that its interpretation of the natural language command aligns with what it's actually encountering in the environment. This verification process provides error correction that dramatically improves navigation reliability. The experimental validation required creating an entirely new evaluation framework called GOAT Core, a carefully curated dataset designed specifically for multimodal open vocabulary multi-goal visual navigation. The results are impressive by any measure. LagMemo's memory module enables effective multimodal open vocabularization for LagMemo. The results are impressive by any methods in multi-goal visual navigation scenarios. But the real significance goes beyond specific performance numbers. This work represents a fundamental shift toward more natural human-robot interaction paradigms, where robots can understand and respond to the kind of casual, contextual instructions that humans naturally give, removing one of the biggest barriers to widespread robotic adoption. Looking toward the future, the research we've examined today points toward what I'd call the domestication of robotics, where robots transition from industrial tools to everyday companions. Just as personal computers evolved from room-sized machines, operated by specialists, to devices that sit comfortably on our desks and in our pockets, robots are evolving from factory-bound automatons to systems that can navigate our homes, understand our requests, and assist with daily tasks. Think of it like the evolution from calculators to smartphones. Calculators made arithmetic faster and more accurate, but smartphones fundamentally changed how we interact with information and each other. The integration of natural language understanding with spatial reasoning suggests robots that can serve as genuine assistants in complex, dynamic environments. The elimination of dependence on expert demonstrations points towards systems that can learn and adapt more rapidly to new situations. The advances in multi-robot collaboration hint at coordinated teams that can tackle challenges too complex for individual systems. Perhaps most importantly, the emphasis on safety and real-world deployment considerations suggests that we're moving from laboratory curiosities to systems that could genuinely be deployed in human environments. As we wrap up today's deep dive into the cutting-edge world of robotics research, it's clear that we're witnessing a fundamental transformation in how robots perceive, understand, and interact with our world. From systems that can navigate using natural language to frameworks that eliminate the need for expert demonstrations, from robots that can juggle multiple conflicting tasks to teams that can collaborate seamlessly, the advances we've explored today collectively point toward a future where the boundary between human and artificial intelligence becomes increasingly blurred. The 12 papers we've examined represent more than just technical achievements. They're stepping stones toward a world where robots serve as genuine partners in human endeavors. The researchers behind these breakthroughs aren't just pushing the boundaries of what's technically possible. They're reimagining the fundamental relationship between humans and machines. What excites me most is how these advances address not just the technical challenges of robotics, but the human factors that determine whether these systems will actually improve our lives. By enabling robots to understand natural language, learn from minimal examples, and adapt to complex dynamic environments, researchers are creating the foundation for a new generation of robotic systems that could genuinely enhance human capabilities rather than simply replacing them. This analysis was created using advanced AI synthesis techniques to bring you the latest insights from cutting-edge robotics research. The content synthesis utilized Claude's Sonnet 4 model for comprehensive analysis and interpretation of the research papers. Text-to-speech synthesis was performed using DeepGram technology to ensure natural, clear audio delivery. Image generation was accomplished through OpenAI systems to create relevant visual content. All analysis underwent human expert review for accuracy verification, though some oversights may exist. Complete references to all original research papers are provided for your further exploration. This multi-stage AI-assisted approach allows us to rapidly process and synthesize complex technical content while maintaining academic rigor and accessibility for our diverse audience of researchers, developers, and technology enthusiasts. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. I encourage you to dig deeper into these papers yourself. The full research is available through the usual academic channels, and each paper offers insights that we could only scratch the surface of today. Share your thoughts about which breakthrough excited you most, or how you think these advances might change your daily life. The future of robotics isn't just being written in research labs. It's being shaped by the conversations and ideas we share about what we want that future to look like. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.